My work was challenging. It was very interesting. I felt a lot of times like I was playing.
It gives you the opportunity to make the connection between what you're learning in class and what you're going to learn in the real world in a job course.
It allows you to see what you're doing and see how it's being implemented and actually see the change that you're working to create.
I don't really get to do too much collaboration in school. It's mainly just individual projects, so also working with others has been super important. I've never really done that before.
It was the first place that I felt like I belonged, and the first place that I felt that my crazy ideas weren't so crazy.
This experience for me has really been phenomenal. I've made some great friends, had a fantastic summer, great networking opportunities, and the projects you get to work on are like nowhere else.
Welcome everyone to this year's Engineering Career Days event, virtual for the first time. I'm Lindsay Thornton, and I'm an education specialist out at NASA Langley Research Center in Hampton, Virginia. And I'll be your host for today. Today's event is a collaboration between NASA Langley Research Center and Jefferson Lab and Newport News Shipbuilding. We also have an exciting team challenge later today provided by Lawrence Livermore National Laboratory. And we'd also like to thank the Peninsula Engineers Council for sponsoring this event each year. Now, joining me today is Dr. Jennifer Gruber, the cross-program integration lead for the Artemis Human Landing System at Johnson Space Flight Center in Houston, Texas. Jenny earned a Bachelor of Science and a Master of Science in Aerospace Engineering from Boston University. And during her time at BU, she was a cooperative education student at NASA's Johnson Space Center. She then earned her PhD in engineering science from Oxford University, where she was a Rhodes Scholar. Jenny, thank you so much for joining us today. We are so excited to have you and hear your story.
Thank you, Lindsay, and I'm excited to be helping kick off this Career Days event. Good morning to the students. I'm honored to be speaking to you at the start of your careers. I hope that many of you will choose careers in science, technology, engineering, and math, because our society has a lot of problems and goals that have STEM solutions and will require our finest minds. Whether attacking climate change, disease, terrorism, lack of access to clean water, good healthcare, or even NASA's audacious goal of building a base at the South Pole of the Moon and moving on to explore Mars with humans. I hope that many of you will use the science, math, technology, and problem-solving talents that you have. If you are attending this event, it's because someone recognizes those talents in you. And I hope that you'll find a way to have a career where you can contribute to society in the best way using those talents. I also hope that some of you will come to work for NASA. In order to help you better understand how to engage in a career of science, technology, engineering, or math, I'd like to tell you a little bit about myself. I have a slide presentation. When I was growing up in Omaha, Nebraska, which is represented there by the red arrow pointing to where Omaha is in Nebraska on this map of the United States, I never imagined that I'd be making this contribution to NASA and having the STEM career that I have. I grew up in a trailer park. I got free school lunch. My dad was a bricklayer, and my mom went to college when I was 8, and she already had 4 children to look after. Many of the teachers and administrators that I had throughout my elementary and junior high and high school career didn't believe in my potential, but I did have the occasional teacher or administrator who did see my potential in math and science and my strong leadership ability and encouraged me. So I want to take a moment to address any educators that are attending this event today and point out just how critical you are to your students. You have the ability to impact them in either a positive way or a negative way, more than almost anyone in their life except for their family. So I do want to acknowledge you and the huge responsibility that you have to help our students work to their full potential. I certainly understand that personally in my own life. When I was about 7 years old, I went to see a movie called The Right Stuff. And The Right Stuff is about these 7 men. They're called the Mercury 7. They were NASA's original astronauts. For those of you who are history buffs, I also encourage you to look into the Mercury 13. They were an incredible group of women who were also being tested for astronaut capability at this time. So when I saw this movie about these men, I was very excited and inspired because I always loved space and looking at the stars, and I'm an explorer at heart. So I told a lot of people that I wanted to be an astronaut and that I was going to study astrophysics. And my family and some of my teachers supported me in that. One of those teachers was my 6th grade teacher, and he taught me extra math when I would finish my assignments quickly and encouraged me in my dream. When I was in junior high, 7th and 8th grade, I did face a bit of discouragement. And by the time I entered high school, I wasn't sure that I was going to follow that dream and go to college. Luckily, my 11th and 12th grade math and science teachers were very encouraging, and as was my 11th grade world history teacher. All of them pointed out to me my abilities in math, science, problem solving, and my strong leadership ability. And my AP physics teacher in 12th grade told me about engineering. Engineering is a career where you use math, science, and problem solving, which are all the things that I'm good at. So having that experience and that encouragement, as Lindsay said, I was able to go to Boston University for my bachelor's and master's degrees. And when I was in Boston and I was studying with engineers, I sort of found my people. I realized that this was a place that I really fit. And even though I did have some challenges with paying for school, and I did experience some sexism because engineering is still a predominantly male career, I did get a lot of encouragement from my college professors. I was encouraged in my studies and also to be a cooperative education student at NASA Johnson Space Center. And with that encouragement and experience, I was able to apply for and got selected as a Rhodes Scholar and able to go to Oxford for my PhD, where I studied ion engines. And the picture in the lower right-hand corner there is a picture of my engine that I got to work on. With all of that behind me, I showed up at NASA and I started out working in Space Shuttle Mission Control, and that's the picture in the upper left-hand corner there. And when you work in mission control, you use your engineering and problem solving and strong leadership abilities. So I had a lot of managers who were encouraging me and helping me to be the strongest leader possible, so that once I was done with my career in mission control and I applied to be a manager, I was selected. And the picture in the lower left-hand corner and the center are pictures of the people that I led when I was a manager. And I continued to gain experience with problem solving and leading teams to do problem solving that led to me being selected in my current position, which is as the cross-program integration lead for the Human Landing System. The pictures here on the right of the slide are the various options for the Human Landing System. Right now, there are 3 companies competing, and we are hopefully going to select 1 or 2 to try to get us to the moon in 2024. Because I had this dream of being an astronaut, and because I went after that dream, even though I'm not currently an astronaut, I have a really great life. In addition to this work that I do at NASA that I'm very passionate about, I also have a wonderful family, and I'm able to help take care of and support my son. And I have a much easier life now than I had when I was growing up. So I'm very grateful that I was inspired to have the dream that I had, and that I had people encouraging me on that dream. So having said that, just a few words of advice for y'all as you start your careers. There will be people who see your potential and unique talents. Some of those people have asked you to be here today. And there will also be people who underestimate and dismiss you. And it will be upsetting. Like I said, I had challenges because of my socioeconomic status and my gender. And at times it was very hurtful and difficult to get past. But I encourage you to embrace the people who encourage you and to work around the people who discourage you. To understand that failure is a part of success. If you stumble, get back up stronger. And I hope that you will continue to work hard and to get past your challenges and follow your calling. I'm excited for y'all as you start following your calling here with this Career Days events, and good luck with your projects. And thank you for giving me this opportunity to speak to you today.
Thank you, Jenny. We really appreciate you coming down and telling us your story and sharing your experiences. And you're absolutely right. Sometimes it just takes one person saying, I think you can do that, for someone to feel like they can. All right, students and teachers, join us next for Fun with Physics with Dr. Larry Weinstein from Old Dominion University.
My work was challenging. It was very interesting. I felt a lot of times like I was playing.
It gives you the opportunity to make the connection between what you're learning in class and what you're going to learn in the real world in a job course.
It allows you to see what you're doing and see how it's being implemented and actually see the change that you're working to create.
I don't really get to do too much collaboration in school. It's mainly just individual projects, so also working with others has been super important. I've never really done that before.
It was the first place that I felt like I belonged, and the first place that I felt that my crazy ideas weren't so crazy.
This experience for me has really been phenomenal. I've made some great friends, had a fantastic summer, great networking opportunities, and the projects you get to work on are like nowhere else.
All right, students and teachers, join us next for Fun with Physics with Dr. Larry Weinstein from Old Dominion University. Over to you, Larry.
Thanks, Lindsay. Welcome to the Physics Fun Demo Show, everyone. My name is Larry Weinstein in the physics department at Old Dominion University. This is my lovely assistant, Perry Neera, and we'll be demonstrating some of the wonders of physics for you over the next few minutes. So what I want to start with is the seat of nails. This seat has several hundred sharp nails on it, and well, you know, people will tell you that you need to be getting that really spiritual frame of mind in order to sit on a seat of nails. But it's actually really just physics. You just sit down, there you are, and you're just fine. Now, what I like to say when I invite people up to try the seat of nails is I ask them, have you sat on a seat of nails before? Most people will say no. And I'll say, try the starter seat. It only has one nail. That gets the point across. Because with 300 nails, it spreads the force out over all 300, and I can sit on it just fine. Speaking of pressure, the next thing that I want to look at is water pressure. So what I have here is a pan balance, and it's balanced. I've got mostly balanced. There's a beaker of water on one side, there's weights on the other, and you know, if I put a little force down here, that goes down. If I put a little force here, that goes down. The question is, and think about it before I do it, if I put my finger in the water without touching the sides or the bottom, what's going to happen? This side can rise up, it can stay the same, or it can go down. Think for a couple seconds. Here we go. So I put my finger in the water without touching the sides, and it made this side heavier. How'd that happen? Well, my finger's pushing down in the water. My water's pushing up on my finger, so my finger's pushing down on the water, so it's adding force to this side, and it gets heavier. So the question is, what happens if I put a piece of cardboard over this cup and turn it upside down? So here we go, piece of cardboard, uncupped. Oh, it doesn't stay. But if I fill the cup with water, and then I flip it over, then, oh, wait a minute, the cardboard's staying. How'd that happen? Well, right now there's lots of water inside, but there's air pressure, and air pushes really hard. There's a vacuum up top, so we've got some water pushing down, all the air here pushing up. If I can let air into the inside, then it lets go. So on the nature of how hard does air push, we want to take a look at how hard air pushes. So here we have an empty sphere, nothing inside. Well, that's not quite true. There's air inside. And so if we can in fact replace the air with nothing, with a vacuum pump, and that's what we're doing now, is we're sucking the air out, turning on the vacuum pump. Here we go. Pulling out the air. Now I'm going to close this valve, and we'll turn off the pump, disconnect it, and now it doesn't come apart. And in fact, we can pull really hard, and it's not going to come apart until, watch out now, I open the valve, let air back in. So if I've got air inside pushing out and air outside pushing in, it's really easy to pull apart. If there's air outside pushing in, nothing inside pushing out, then we can't pull it apart. So let's take a look at this with a soda can, because that thing's made of steel. It's pretty strong. We're going to do it with a soda can, which is not very strong. So let's see what happens. So the first thing I need to do is to light my propane torch. Now I'm going to take just a standard empty soda can and put in a little bit of water. Not too much. Not even an ounce. I'm going to take a sophisticated vacuum valve. This is called a piece of cardboard. put it over the top, just to block the path a bit. Then I'm going to heat it up. I'm going to put it in the propane, and the propane is going to make the water boil. When water boils, it takes 1,000 times more volume, and now I've got air on the outside pushing in, I've got air on the inside pushing out. I've got air on the outside pushing in, I've got water vapor on the inside pushing out. You can see it's boiling furiously. If I can get rid of that water vapor, then the can crushes. Because once I dunk this can in the water, all the water vapor that was inside condensed. I had air on the outside pushing in, nothing on the inside pushing out, and the can went crunch.
All right, so continuing with this idea of what can we do when we heat things up, I've got two balloons here. One's just filled with air, and one's got a little bit of water in it. So you can hear that. All right. What I'm going to do is heat them up. Take my candle. All right. Bring my balloon in nice and close, and see what happens as the rubber in the balloon starts to heat up. Suddenly it pops. All right. So let's try that again. Let's use the water balloon. So this time, all right, same type of material, but it's got a little bit of water in there. Bring it towards that flame. What's going to happen here? Am I going to make a big splash? Nothing's happening. Why is that? Yes, with the previous balloon, the candle was able to heat up the plastic, melt it a little bit, cause it to pop. But here, there's that water that's inside the balloon. And so we're heating up the water as well, preventing the rubber from reaching that critical limit where it suddenly fails and pops. So we've got a camera aimed at me so that you can see how I'm glowing in the infrared spectrum. You can see different objects on me, like I've got a pocket protector here. Nice and cold. Go to my exposed skin, nice and warm. So let's see what kind of thermal objects we can play with here. I take myself in view, got myself some cups of ice. Let's aim at that thing, right? So I've got cups of ice. You see how they're that nice dark color in the camera? It's because of how cold this is. The temperature setting is scaling these away. Now if I switch to something like nice thermostat, warm water, you can see down here in the cooler region, right? This thermostat is trying to keep the hot water that's inside the cup contained. But you notice up here, see how it's a little bit warmer? Because that water is escaping, right? Should be good to pour. There we go. All right. As I pour that hot water, you can see that wonderful temperature changing, moving around the cup. Throw some ice in there, start melting it. What are the other things we can do with this camera? We can talk about how visible an object is to the infrared spectrum. Because the camera that you're seeing me at right now is looking at the visible spectrum. And I've got a black bag here. If I was to stand in front of the bag, you wouldn't see my face. But I look at the infrared camera, take that black bag, and you still see my face. Try and wiggle my eyebrows if you can see that. Right. So even though on camera, in the visible spectrum, this bag looks opaque. It looks like you can't see it. To the infrared, the rays go right through. What about this? Got myself a nice piece of glass. On that camera, you can see me nice and easy. Bring it over here. And I've blocked myself out. Take out my heart, right? Go back to my face, right? So here's material, here's an example of something where in the visible spectrum, right, the light's able to transmit through, yet something in the infrared, the temperature we tend to associate with warm, hot objects, it's completely opaque, completely blocks out. Try writing messages on this. We've all heard this idea that warm air rises, and so what we have here is a strange type of beaker. It's filled with liquid. I'm just going to put a little green dye in there, give it some color. All right. So you can see that the liquid is pretty stationary. What I'm going to do now is introduce some convection. I'm going to heat up this corner here. We'll try and just get this corner here nice and warm. And we'll start to see how as the water gets hotter here, let's get that a little bit closer. We're going to start to create a flow. You can see how the currents are being generated here. That warm air, in this case though, warm liquid, is being pushed up into a less dense region of the tube. As it rises, it tends to cool off, come back here, start to fall. And now we've created this convection, right? We've created this cycle of the warm material rising up and flowing things around in this circle. All right. We've almost completed our first loop. And we can keep this going on. Take the heat away. You can start to see where the warmest regions is as it's trying to convect around, flow. Let's get me out of the way.
Okay, so the next thing that we want to look at, Perry, if you would take this away, please, is we want to look, since we started looking at moving fluids, we want to look at what happens when the fluid, which can be a liquid or a gas, moves quickly. So for this, I'm going to take off my mask. And the question is, what happens when air moves quickly? Well, there's an easy demo I can do. I can just blow over the top of a piece of paper. And if I do that, you think, well, gee, the air's rushing out, it's going to push the paper down. It doesn't. The paper rises up when I blow on the top side. And that's because a moving fluid actually has less sideways pressure than a non-moving fluid. And this is part of the reason why airplanes fly. It's a bit more complicated, but this Bernoulli effect is part of that. And we can see that with something else, where I'm going to take this blower to give me a current of air. This blower is blowing air straight up, and I can suspend this ball in the current of air. Now, that's not terribly surprising, because the air is pushing up, gravity is pulling down, but I can also tilt it a bit, and it's staying in the airflow. That is weird. Now, if I tilt it too far, it falls out, but it's staying in that airflow, and it's stable, because the air going up, it's fastest in the middle of the flow, there's the least pressure, and the ball stays where the pressure is the least. I can demonstrate this another way. I have here a complicated scientific device where when I blow into it, I make a current of air going up, and the eyeballs stay suspended. The last way I can do this is I have a funnel and a ping pong ball. And if I put the ping pong ball in the funnel, it's not going to stay there. But if I can blow through the funnel, wait a minute, you're thinking he's blowing down and it's going to make the ball stay up? How does that work? Well, like this. As long as I'm blowing, that ping pong ball is staying up, and the reason for that is that the fast-moving air has a lot less sideways pressure than the regular air. There's less pressure up here where the air is moving really fast, more pressure from below. The ping pong ball stays up. That's called the Bernoulli effect. We can see another couple examples of what that does. So, take it away, Perry.
I've got here what we call an air cannon, right? Just a little spring-like area. I'm going to spray some smoke in here, or just a can of smoke, and start seeing what happens when we have some flowing air. So let's fill that up for a bit right now. Just get a nice, decent amount of smoke up into this thing. Keep going for a little bit longer. Let's start there. We'll try and go across the camera. Get ourselves these wonderful smoke rings. Do one shot at the camera. And you can see that you get this actual ring shape of the moving smoke cloud due to the cut off of the shape here. So, another one we can do. Start applying Bernoulli's principle. All right. We talked about how I can reduce the pressure in a region. So what I'm going to do is use my can of air, my air cannon, to knock these things down. So let's get my aim right. I'm aiming right between the two. What happens when I hit? They moved in. We'll set that up one more time, but a little bit more space between them. All right. So I'm not aiming at a cannon. I'm not trying to knock one down. I'm going in between and seeing what happens to those soda balls when that rush of air flies by, reducing the local pressure. That flowing air, when that air is in motion, the pressure around it is reduced. So some other things we can do with this. All right, we're trying to exploit the objects moving in air. Right? Did anyone ever thrown a curveball? What's the trick? You take your baseball and you gotta give it a good spin. Well, I'm gonna cheat. I have myself here, a nice little thrower here, got some sandpaper in it. That allows me to grip this really well and give this ball a nice, great spin. Let's get this camera out of my way. What I'm gonna do is try to give it a spin. I'm gonna throw it straight like that. Watch the curve of the ball. So notice the curvature of the ball. That rotation is changing the air pressure around it. So we'll try to throw at the camera, and I'm going to curve it sideways. So again, so I'm throwing at the camera, and we see the curve. One more. And we see the curve caused by that rotating object to cause it to arc in the air.
Okay, so we've been looking at heat, we've been looking at moving air. Let's go back to heat and take a look and see what materials do. We already said when we heat water, it expands, it becomes less dense, it rises. And we saw that with the convection. Here what I've got is I've got a plate, I've got a ball. The ball does not fit through the plate. So the question is, what happens when I heat up the plate? When I heat up that aluminum plate, aluminum is going to expand. So here's my aluminum plate. I'm heating it up. When the aluminum expands, is the whole inside going to get bigger or smaller? So I'm heating this up, and am I going to be able to get the ball through the hole in the plate once I've heated this up? So it'll take me a few more seconds to heat it up. I've got a lot of aluminum here. It's a fairly thin plate, but it's fairly large. And so we've heated up the aluminum plate. And when the plate gets bigger, the hole gets bigger too. Huh, interesting. So what happens is that when the aluminum plate expands, it's kind of like blowing it up on a Xerox machine. The outside gets bigger. Yeah, I touched it, I'm an idiot. The outside gets bigger, it's hot. The inside also gets bigger, the whole thing gets bigger proportionately. Now, the other thing we've looked at before is we've looked at air pressure. And what we've said is that, great, thank you, air pushes really hard. And so what I've got here is a thing called a vacuum cannon. Here's my projectile. It's a ping pong ball. I'm going to drop it down. There's nothing inside this. This is just an empty PVC pipe. I've got an inlet here so I can use a vacuum pump and suck the air out. I've got a piece of aluminum foil on the end. That's my vacuum seal. Not very strong, you're thinking. You're right. And here, on this end, I've got the top of a soda can, and I'm placing it on. And now, this is reasonably airtight. So I'm going to take the vacuum pump, plug this in, and before you turn it on, we're going to pump it down, and then the aluminum foil is going to rupture. That ping pong ball is going to come flying out. You'll hear that impact. Go ahead and turn it on. So here we go. And the ping pong ball shot out, hit the wall, bounced over there. The first time I did this, I did it in a middle school auditorium with a racquetball. The racquetball hit the far end of the auditorium with such an audible thwack. I was grateful I hadn't hit any of the students. That could have been interesting. So, we've now looked at what happens with pressure, that air pushes really hard. We've looked at temperature, that heat makes things expand. We've looked at water, that water can absorb a whole lot of heat. The next thing we're going to do is we're going to look at extremes of cold. So now what we're going to do is we're going to look at the properties of liquid nitrogen. And nitrogen's in the air all around us, but the question is, what happens when we make it a liquid? Take it away, Perry.
All right. As usual for safety, I'm going to use gloves because we're dealing with some pretty chilly stuff. Right. Take my little doer here. I'm just going to pour it out right now. Pour it into this display doer here. Oh. Watch it flow. Oop. You're seeing a mixture of the liquid going into the doer and all this fog around it. That fog is mostly water molecules in the air condensing down. Probably a good amount. Put that on the side. All right. Thank you. So let's take a little ladle, scoop some of that stuff out, try and convince you it's a liquid. And we'll just dump it on the floor, on the tabletop here. You see it instantly evaporating. This stuff is so cold. It's so cold that in our room temperature, it's basically boiling. So we got this constant boiling material as we're flowing around. Right. So let's get some into a nice clear cup. Probably easier just pour it in. Come on. There we go. So you can see how it's constantly, it looks like it's water that's boiling, but that's this liquid nitrogen just constantly evaporating in this area around us. Nice clear substance. You can see as I put it down, it touches that warm table, starts boiling over and over.
So Perry's been referring to this as really cold, but the question is it cold or hot? I've got a tea kettle. Now, when tea kettles whistle, it's because they're really hot, right? You put a tea kettle on the stove, you put water in the tea kettle, and what happens is that when it gets really hot, it whistles. So the tea kettle is whistling, thus it must be really hot. Well, what's happening is the liquid nitrogen for us is really cold. But because nitrogen boils at a very low temperature, to the nitrogen in the tea kettle, the surroundings are really hot and the nitrogen is boiling away. So just to show you what it looks like, we have a thermometer here, and we're going to take a look at what our temperatures are. So here we are. This is sort of the range where we live. 0 degrees Fahrenheit is really cold. Here's body temperature, 98.6. Up at the top, water boils. But we pretty much live here. But we have to come all the way down to here for liquid nitrogen. Liquid nitrogen, minus 320 degrees Fahrenheit, 77 Kelvin. That's 77 degrees Celsius above absolute zero. Liquid nitrogen is closer to absolute zero by far than it is to where we live. So this is 2/3 to 3/4 of the way to absolute zero. This is really cold stuff. So the question then is, what would happen if Perry put his finger in the liquid nitrogen? Now, Perry, unfortunately,
I'm not volunteering.
is not volunteering. However, we have flowers that have volunteered to do this. So Perry, if you want to take 2 of the flowers.
All right. Let's get them nice and cold now.
You can hear the boiling. The flowers are really hot. They're 300 degrees hotter than the boiling point of liquid nitrogen, making the nitrogen boil. When the boiling sound stops, then we know the flowers are at liquid nitrogen temperature.
Almost there. I'll give one to you.
Looks fine, doesn't it?
All right. Brush it. There's
Yeah.
All right.
But it's very brittle. If I took a regular flour and I crushed it like that, it would be fine. This one, frozen. So the next thing we can look at is what happens if I put a match in liquid nitrogen. Now, there are a few different things that the match could do. The match could burn brighter. The match could not burn as much. Nope, just leave it.
That's
I'm
good.
All right. Match could just stay the same. It could go out or it could explode. So which of those do you think the match is going to do? Here's my match. Just in case it explodes, I'll be down here. And you notice that the match went out. Why did it do that? Well, I didn't put it in the liquid nitrogen. The level of the liquid nitrogen is down around here. The match only went into about here. I can put my hand in here. No problem. It's like reaching into the oven to get cookies. Air is a very poor conductor of heat, so you can reach in and put your hand in the oven. As long as you don't touch any of the metal bits, you're fine. So let's take a look. The way we'll take a look now is I'm going to put some more liquid nitrogen in this cup. And then, Terry, while I'm doing this, if you would refill the dewar, please. And you can see that liquid nitrogen is boiling away. We've got a couple carnation petals in there. Here's another match. What I can do, this cup is full mostly of cold nitrogen. So if I pour it out onto the match goes out. So the match went out not because it was so cold, but because there was no air. And all the liquid nitrogen that was in the dewar that was boiling furiously was turning into cold gaseous nitrogen. And so the dewar is full of liquid nitrogen in the bottom. The top 3/4 was gaseous nitrogen Flame needs oxygen. There was no oxygen. Same thing here. Liquid nitrogen in the bottom, gaseous nitrogen in the top, and I can pour it out. And that fog, the water vapor, shows us where the liquid nitrogen, or where the gaseous nitrogen is flowing. Now, one of the things we're going to want to look at is how different materials behave when they're cold. So I've got a racquetball. I've got a ping pong ball, and I've got a super ball. The next thing I have is I have a pewter cup here that I can hold it by the handle, and it's pewter, so it's a beautiful bell, right? Clunk, clunk, clunk. Okay, it's not a very beautiful bell. Maybe we can change that. So we'll put the pewter cup in the liquid nitrogen, and we're putting them in now to give them time to get cold. And again, liquid nitrogen evaporates really quickly, and all this fog here is the same fog you see in a cold day when your breath condenses.
All right. So we're going to give those objects a couple of minutes to cool off, start getting down to that cold temperature. In the meantime, let's bring back to our concepts of what's happening to pressure. Like when I say I've got a balloon. What happens to the balloon when I introduce it to the liquid nitrogen? What's going to happen? All right. Go ahead and bring it in. The air inside the balloon is getting cold. Oop. Cold air reduces the pressure. As soon as I pull it up, you can see it start to expand again. It's starting to come back to room temperature. Come on.
Okay, now put it in and leave it in.
Now we'll just...
Let's see what happens when it gets really cold. So you notice that as it gets colder, the air's volume's decreasing, the pressure's decreasing, it's getting smaller and smaller. Just let go. Just let go. Yep, just let it go.
Oops, sorry.
And the other thing is that, well, this is liquid nitrogen. The air in the balloon is oxygen and nitrogen. The oxygen is liquefying. The nitrogen is also liquefying. So, in fact, there's just a puddle of liquid air at the bottom of this balloon. But as it warms up, it becomes gaseous again, and it expands, and looks like it's doing okay. And in fact, if I heat it up with my hand, then it's going to expand even faster. You notice I'm heating it up with my gloved hand. Need to be careful here. Now, one of the things that happens is that, we put the balloon in the liquid nitrogen, it got really small, it got really cold, we warmed it up again, it's fine. We put the flour in the liquid nitrogen, and you can see that this flour was never in liquid nitrogen. This flour, which was frozen and warmed up again, it's warm now, doesn't shatter, but it's looking pretty darn sad. So if you had any thoughts of immortality, having yourself frozen in liquid nitrogen in order to be revived later, you'll come back like this really sad flower if you're not very careful. The reason for that is the cells in the flower, the cells in our body, have cell membranes and cell walls. When it freezes, it makes ice crystals, breaks the cell walls, breaks the cell membranes, turns the cells into mush, and no, they're probably not going to be able to revive you 100 years from now to cure whatever ailed you. Okay, so.
Going back to, we saw when we chilled the balloon, how it collapsed. Let's see what happens when we let that liquid nitrogen, thank you, when we let the liquid nitrogen sit in a closed container. Oop, I want the ping pong ball. Keep getting it.
More than that.
Yeah, I need a little. There we go. So, not even sealing it. You can see how it's constantly expanding outwards. That gas, as it's evaporating, is pushing out. So now we're going to seal it. So what happened? I trapped the gas. The gas inside is constantly evaporating. The pressure is building up inside the soda bottle until finally the seal breaks and it pops.
And so the other point to make is what makes an explosion is not the expanding gases, but the fact that they're confined. So when I just put liquid nitrogen in this cup, it boiled away, no problem. But if I put liquid nitrogen in this bottle and seal it, then the pressure is going to build up until it releases somehow, and depending on how tightly it's sealed, that can be a really big boom. Liquid nitrogen, yeah, we'll just dump some out. So, what we have then is we have a few balls, and okay, we've got the racquetball, feel that later. Put that back. Ping pong ball. What happens to a really cold ping pong ball? Does it bounce higher? Does it bounce lower? Does it shatter? Well, it's a ping pong ball. It's basically just like it was before. No problem. Let's take a look at ball in here, a super ball in here somewhere. Okay, super ball. Is it going to bounce higher, bounce lower, or shatter? Well, super ball is not bouncing. So the super ball became a lot less elastic. Last, let's take a look at the racquetball. So, racquetball, going to bounce higher, lower. There, it just bounces, doesn't bounce, but what will happen is if it hits something hard enough, it shatters. Carpet that I hit it on the first time wasn't. And then, last of all, we've got the pewter cup, which, remember, it gave off such a lovely thud last time. Now that it's been really cold, it's a nice bell. So with that, I thank you very much. Thank you for joining us. Take a quick break. We'll be back at 10 o'clock with the engineers panel. Thank you.
All right, welcome back, everyone. Thanks for joining us this morning. With me today are 3 engineers, one from each of the organizations that help collaborate to put this event on every year. Joining me today from NASA is Carrie Bean. From Jefferson Lab is Will Oren. And from Newport News Shipbuilding is Tim Herbin. Thank you guys so much for joining me today and answering our questions. Before we get started with questions, though, I want to give our second for you to tell our students a little bit about yourselves and what you do. Carrie, why don't you start, ladies first?
All right, so as said, I'm Carrie Bean. I'm a systems engineer at NASA's Jet Propulsion Laboratory in Pasadena, California, and I have 2 different jobs at JPL. First, I'm the deputy lead rover planner for the Curiosity Mars rover. And sorry for my cats in the background. One's Misty, one's Pinto. You'll see them around. But as a rover driver, you know, I get to help lead the team in driving the rover. We also operate the robotic arm, so that's pretty fun to do on a almost daily basis. And then my other job is a helicopter integration engineer for Perseverance and Ingenuity. And so I'll be helping the Ingenuity team fly on Mars in the next few months.
Wow, that's amazing. Good luck. I'm sure it'll go amazing. Will, over to you.
Okay, my name's Will Oren. I'm the head of the engineering division at Jefferson Lab. We run a large particle accelerator, electron accelerator, to do nuclear physics experiments. My division's about 160 people, and we are made up of a bunch of engineers and technicians. We design and build the equipment that goes in the tunnel and maintain it and operate it. And just to give you a puzzle, I'm a geodetic engineer, so you can ask me about what that is later.
Great. That's awesome. All right, Tim.
I'm not sure how to follow up a range or a rover pilot and a particle accelerator. Wow, that's amazing. But excuse me, I'm Tim. I work at Newport News Shipyard, and I do cybersecurity for them. We mainly protect the sensitive information that's entrusted us with the government. So we just make sure that there aren't any breaches or anything else. We try to keep the bad people at bay, basically. And we're branching out from Blue Team, which is mainly protecting the network and everything contained wherein, to a more Purple Team, which has a little bit more offensive capabilities too.
Wow. So do you walk around in like a trench coat and sunglasses, or?
I did that the first day. They told me to not do that again.
Awesome. Well, it's so great to have the 3 of you on. You all have amazing jobs. So I'm just going to go ahead and start in with our questions. Carrie, can you tell us, when will Perseverance and Ingenuity reach Mars?
So they will reach Mars on February 18th, which is not that far away. So.
And how do you feel about that?
Nervous. I am just a very interested observer. You know, we can't do anything once it gets there. The signal takes so long that they'll be on the surface by the time we even find out that they started entering the atmosphere. So we are waiting with bated breath.
Sounds nerve-wracking. Now, what about Ingenuity? Can you tell us a little bit about Ingenuity?
Yeah, so Ingenuity will be the first time that we're flying on another planet. And so right now it's attached to the belly of the rover. And once we land on Mars, we will deploy the helicopter, and then we'll get 30 days to fly the helicopter around on Mars and see what it's like, so we can potentially build a future mission to fly around on Mars.
Awesome. All right, Will, tell us a little bit about the accelerator at Jefferson Lab. That's a really exciting thing to have. It's no small, no small feat.
So our accelerator is pretty unique. It was the first of its kind with the scale it was built at. The accelerator sections are actually cooled to 2 degrees Kelvin. We have the largest 2-degree Kelvin refrigerators in the world, 2 of them. And the reason you do that is to to make the structure superconducting. And when you do that, we can accelerate beam through it continuously and at a very high power. So we actually create beams that are megawatt in power, and run them into targets and watch what happens, basically. And the targets tend to be like liquid hydrogen or highly compressed or cooled helium. So they're very elementary particles that we can look at the scattering off the neutrons and the protons in the nucleus. So anyway, the accelerator is, when you stretch it all out, it goes around in a circle, multi-pass, and when you stretch it all out, it's about 5 miles long. And anyway, we go up to 12 billion electron volts. That's how far we can accelerate it, or how high an energy we can.
Awesome. So what types of engineers work with you?
Well, so we have mechanical engineers who do lots of structures. We do a lot of work in thermodynamics with the 2 degrees Kelvin. So I have folks that are specialists in refrigerators, so what we call process engineers. Many electrical engineers, because you can imagine all this stuff is automated and many control systems to go. Lots of high power. We have 2,000 horsepower motors in the cryogenics plant. You have people like me who are geodetic engineers, and we actually do the alignment of the components. So these magnets to guide the beam have to be aligned to about 1/10 of a millimeter relative to each other. So it's kind of, so there's a whole gamut of engineers that we use.
Excellent. That's a great example. I just want to point out that all of our different institutions use a variety of different types of engineers. You know, not everyone knows there's so many different types of engineers, and whichever type you prefer, you know, if that's something you'd like to do, you know, you can find a place at any of these 3 institutions. So Tim, tell us, how did you get to be the cybersecurity guy?
It's a funny story. Well, it's not so funny. I spent 21 years in the Navy, and I did a lot of different missions, went a lot of different places, but I've always had that need, that desire to, I guess, protect. And when I retired from the Navy, I didn't know what I wanted to do when I grew up, basically, because now I have to get a big boy job. And I flew drones at a startup company in Virginia Beach, but it just really wasn't paying the bills. And I was going to school for cybersecurity expert engineer, I guess, because it's that innate protection kind of thing. I want to defend. I want to make sure, you know, that our interests are protected and no foreign government is trying to get into the cookie jar, if you will.
Excellent. Well, we definitely appreciate that. I can speak for everybody on that one. All right. So Carrie, tell me, when you're driving on Mars, what does that really mean?
Yeah, so most people think, you know, we're sitting there in real time with the joystick driving around, and that is not what we do at all. So we typically plan the rover activities 1 to 3 days at a time. And so we come up with essentially a to-do list for the rover of take pictures here, do this experiment, and then we come up with a series of commands to drive the rover to a specific location or to use the robotic arm to put its instruments down onto specific rocks. And so we have to think through in advance of what could go wrong. And so you have to be able to set your safety checks. So if the rover detects something is wrong, we'll go ahead and we'll, protect against things like maybe we don't want to go over a really high rock or something like that. And so we'll make a list of commands of drive here and then go around this rock to drive over here. And, we'll send it, the rover can drive for a couple hours at a time if we really want to. And then we don't find out what happens until maybe the next day or a couple days later. So it's an interesting thought process of how do you think about what the rover might do as you're driving along. So.
Right. I'm sure that requires a lot of planning.
Yep.
All right, Will, tell us if we want to, maybe not do exactly your job, but if we'd like to come work at JLab, what would a student need to do?
Well, I think first off, before you think about even coming to JLab, a student needs to do something that is interesting to them and they can be enthusiastic about. And so that you find that niche that you're very good at and you enjoy doing. And frankly, that will come out in your interview if you come to talk to us. If you're a mechanical engineer or electrical engineer and you're enthusiastic, one of the first questions I always ask is, why do you want to do this? And you better have a good answer for that one. And so I guess what I'm trying to say is kind of know who you are and where you want to go. And whether it's in mechanical engineering, electrical engineering, or process engineering, or geodetic engineering, why are you doing this? And think about that. So that would be my advice.
How did you decide to become a geodetic engineer?
Oh, that's in the story. So I'm good at math and I like working outside. And so I ran into this idea of becoming a land surveyor. So I went to school to Purdue and got a bachelor's in land surveying. But as I learned more and more about land surveying, I realized there was this legal component in it that I didn't like. It's not like an equation that you can work it out and it'll always come out the same way. But I did like the measurement part of it. So I went ahead and got a master's degree in geodesy. And as part of that, I've discovered this niche of industrial alignment, where you're doing very, very high precision work. Back in the 80s, this was with big fancy theodolites. And it worked out. I ran into a job out at Stanford University at the Linear Accelerator, and they pulled me out of grad school. And I went and worked there. And it just kind of grew from there. It's a very niche position. So that's something you find in my business. There's often these very niche positions. They're very unique because of the technology we use.
Nice. That's great. That's a great point. Tim, tell us, how did you get where you are? I know you have a long, very cool resume. Tell us maybe a little bit about your path to where you are now.
Sure. Basically, and I won't hold this against Will, but I grew up in Bloomington, Indiana, Purdue and IU,
Kokomo, Indiana.
But I joined the Navy. I felt a need to serve, I guess, and I wanted to just get out of Bloomington, really. And I joined the Navy without ever seeing the ocean. It's actually it's a good thing that I liked it, because you're on the water. You're supposed to be on the water all the time. Kind of how where I got to where I'm at is honestly by luck. I was kind of one of those fly by your seat kind of people, and fortunately everything is really, really worked out well for me. I know that's probably not what you want to hear when students are planning their future, but I couldn't ask for a better career, and the fun time that I had actually while I was in the Navy. The training that they give you is it sets you up for the rest of your life. And that's kind of why I'm here now. The attention to detail, the ability to notice all the small things, especially if you're solving, there's some kind of incident that comes in that we need to check to make sure that someone's not trying to infiltrate our network. It's that problem solving ability that the military really gave me, really helps out where I'm at now, and helps me succeed. I won't say excel because that sounds arrogant, but it helps me do my job.
I think we can say you've succeeded. So what kind of education did you have to get in this position?
I was a late bloomer. I joined the Navy because I actually, honestly, I thought I was just a horrible, horrible student. Growing up there, I struggled a lot. That was before we really knew about ADHD or anything else like that. But and I was always scared to go to college. And going through the military ranks, they always want you to go to school, better yourself. And I was always kind of, I was trying to avoid it as best I could. So when I was retiring, I decided it's time, and I just need to do this. And if I'm, a horrible student, I'm a horrible student. But lo and behold, I was a great student. Like it really surprised me. Going through University of Maryland, I went through them because they have a cybersecurity degree that's actually accredited by the National Security Agency. And I worked there a little bit when I was actually in the Navy. So that's kind of where I went that route, and it just blossomed into this. The bachelor's degree they took a lot of my military credits and put it towards my degree as well. So it really helped out, especially the real world practical learning labs that they have really set me up for success.
That's great. And that's a great message for our students that are watching, because some of them may not be ready to go to college right out of high school, and they may come back to it as adults. And there's nothing wrong with that. Actually, sometimes that's a wise choice. Sometimes you got to live a little before you go back to school. And then some people are ready right out of high school. It just depends on the person. All right, Carrie, what inspired you to become an engineer?
I didn't start out as an engineer. My degrees are actually in meteorology. I grew up obsessively watching the Weather Channel, and that's all I wanted to watch. Forget all the movies, Disney movies, whatever, Weather Channel. That's what I wanted. And so I went to school for that. And in high school, I actually did the whole Florida vacation with the family, and it just so happened to be the week of a space shuttle launch. And so we went and saw the space shuttle launch, and I was like, okay, maybe space is cool. Maybe I'll consider that. And there's so many different things you can do with space. You can be an astronomer, astrophysicist, engineer, all sorts of things. And I couldn't decide, so I decided that I was just going to go to school for meteorology. And that's when I found out you can study the weather on other planets. So that was pretty exciting. So I started working right away on NASA missions at Mars, studying the Martian atmosphere, literally my first week of college. And, I got these opportunities to work on different NASA missions, not only as a scientist, but also operating the cameras on the different rovers. And that was really fun. I really loved that team environment. You still had to have the scientific background to understand what the different scientists were requesting, but you also got to work with the engineers, write up the code that would go to the spacecraft and take those pictures. And so when I was getting ready to graduate, I luckily ended up at JPL and getting to operate a whole bunch of different spacecraft. And so that's kind of how I fell into engineering. I don't do anything related to my degrees at all anymore, but it gave me a really good background into operating Mars rovers, apparently.
Awesome. Hey, life takes you all sorts of places you never expect.
Mm-hmm.
All right, Will, what do you enjoy most about being an engineer?
Well, so when I got to be an engineer, I love building things. I love putting stuff together and seeing, sitting down and designing a way to do something, and then taking it out in the field and actually trying to do it and see it be successful and work. And in our business, it's whether you can drive the beam through the beam pipe that I just aligned and all the magnets, and then it keeps the qualities it was. But as I progressed through my career, somebody got crazy and decided I ought to be a decent manager. So I've done less engineering and overseen engineering. And I tell people, I ask myself why I come to work every day. And one of the reasons I do is I like working with people. And it's fun to see folks build things and get that sparkle in their eye when, oh, it worked. Or oh no, it didn't work. Let's go fix it. So that's what drives me is in this business too. I get to learn something new every day. It's really neat to be working with it's kind of like being the house that doesn't cost so much in a fancy neighborhood. I get all these PhDs I get to work with, and I learn something from them every day. And so that's what makes me come to work.
Excellent. Tim, I'm going to ask you a similar question. What do you love most about your job?
What do I love most? I would say the problem solving. There's no one way to attack there's no cookie cutter type of way to solve each incident or ticket or whatever it is that we have to respond to. Each time is unique every single time, and kind of like just the people I work with, the team I couldn't ask for a better team. And I was on some great teams, some of the finest people the world has to offer in the Navy. But this is one of the best teams at Newport News. They're patient, they respect each other, and it sounds kind of cliche, but those are amazing. It really can foster your own talent and your own ability to learn. But the problem solving and the people that I've met, there's never anything. No day is the same. There's no Groundhog Day. It's always something new they're throwing at you. So I kind of like that.
That's an excellent point. The people you work with do make a huge difference in how much you love your job, no matter how cool it is. Now, Carrie, let's say I'm a student and I'm thinking, oh, I want to do that. How do I get to do what you do or something similar?
Yeah, so certainly some sort of STEM degree is your best bet. Most of the people I work with have some sort of engineering degree, computer science, some sort of scientific field, something like that. But the ability to keep learning is really important. There is no degree you can get that is Mars Rover Driving 101, right? Like that course does not exist at any university, right? And so you constantly have to be able to learn and be flexible and multitask. I have to be able to say, okay, well, if I'm driving over here, I have to remember to do this safety check and I have to be able to do this thing and the other thing. And so having that mindset of, being able to juggle and multitask is another really important thing. And working on your communication skills as well. As everyone has said, working with people is one of the best things. That's certainly one of the best things at my job as well. But you also have to be able to communicate from people all around the world. English may not be their primary language. And so you have to be very clear and concise. And then, engineering is a lot of communication of, here's my design, here's why I think it works. This is my reasoning for it. You have to be able to explain your ideas.
Absolutely. Absolutely. If you can't communicate your science or your engineering, you're in big trouble.
Yep.
Now, Will, can you tell us, is there anything you did as a high schooler that you think really helped prepare you for your future?
Oh, yeah. Learn to write. Learn to write. You got to learn to communicate, and writing is a big, big deal. And I'd actually say that some of that a lot of that's the reason why I'm where I am right now. Now, I was fortunate. My mom was an English teacher. So we spent some long nights learning how to compose things. And I had some good teachers in school. But that if I had to point at any one thing, it's incredibly valuable and will serve you no matter what profession you go into. Learn to write,
Absolutely.
Learn to communicate.
Yeah, that's a really good point. And a lot of people have that bad tendency to go, well, I'm going to go into science or I'm going to go into engineering. I don't really need to know how to write. But like you said, it is actually far more important than people usually realize. And not only writing, but also speaking. So both of those things are always good to have in your back pocket.
Now, I didn't tell you I could spell very well.
That's what spell check is for.
That's right.
How long has spell check been around? Because I feel like
let's just say I have a standard analog dictionary here on the shelf that's very well worn.
Tim, I want to ask you, did anyone when you were in high school inspire you that helped you become who you are today?
I think there's quite a few. My English teacher would actually write different quotes on the board every single day. And although I've never met the man, Teddy Roosevelt, I believe, she wrote up there that said, he was quoted to say, "Do what you can with what you have, where you are." And that benefited me the most, actually, in life-saving situations in the Navy. It's easy to just go, oh, I can't do it, or there's no way. There's always a way. There's always a way to figure it out. And that kind of mindset, doing what you can with what you have, where you are, has really helped out at Newport News. Some of the things that we get, we have no idea what is this thing, and we have to. It'll be like an alert, and like I said, there's no cookie cutter. It's not the same time, or it's not the same way to solve a problem every single time. It could be the same alert, but if you've never seen it before, you ask somebody. If there's no one around, you have the internet to look it up. But yeah, your two hands and your willpower to get it done, that speaks volumes. So Teddy Roosevelt.
Excellent, excellent. All right, well, we're getting close to the end of our session, so I'm going to ask all of you to answer this final question. If you could give yourself, your high school self, any advice, what would you give yourself?
Gosh, I think my number one piece of advice would just be keep going. Things will be hard. I failed my calculus class the first semester of college. You will reach hurdles along the way, but the most important thing is to learn and adapt from them. Constantly I'm learning new things and having to adapt to them at work. So keep learning, keep going.
That's a great point. And you'd be surprised, and I'm sure our students out there would be surprised, how many people that are extremely successful these days had some sort of failure. I talked to an astronaut the other week, and she's like, yeah, I almost failed physics the first time, I got to college. And, everybody has these struggles. Don't think you're alone. And just like Carrie said, keep on going. All right, Will, what would you tell your younger self?
Yeah, it's kind of the same thing. Don't be afraid to challenge yourself and fail. Don't take the easy way. I sometimes wonder whether I should have challenged myself more, and instead of getting A's and B's, we've gotten some C's and D's on some really tough classes. So yeah, I think that would be it. Don't be afraid of challenging yourself and failing every once in a while, because you'll learn a lot when you fail.
And Will, would you say that in engineering, failure is actually a part of the process?
Absolutely. I mean, we do failure analysis, right? We used to have what we called busting lab, where you broke things. So you took them to failure, right? So yeah, there's a certain degree of experimentation that goes with building things, and particularly when you're on the edge of what you're trying to do, when you're pushing the technology that you have, you're going to have failures. Absolutely.
Yeah, we like to say failure at the beginning of a project only means a higher level of success in the end. All right, Tim, what would you tell your younger self?
Up first, I want to work in that busting lab. That sounds awesome. Actually, to build off on the wise words of Carrie and Will here, when I was young and going through high school, I defeated myself a lot. And I came up with this, it's my own. I may have taken it from somewhere else, but success teaches you how to succeed, but failures teach you how to live, what to do. So if you can eliminate your failures and replicate your successes, I mean, you're just going to be a better person, a better parent, whatever it is, a better adult, better functioning member of society, better at your job. And yeah, that's something I wish that I could go back and say, Tim, like, study. You are smart. You can kind of do this. Yeah, that self-defeation attitude was just, yeah.
Yeah. I can be amazed at how many people, even though they're successful, still have that imposter syndrome where they feel like, okay, I'm a successful person, but it's not real. I'm not really this person that everybody thinks I am. I'm not really that good. But you are where you are because you deserve to be there. You're good enough to be there. So don't defeat yourselves. And I think it's about time we wrap things up. I want to thank you guys so much for coming out today to talk to me and to talk to our students and answer our questions. You guys have been fabulous guests and we really appreciate it. And we wish you luck with all of your awesome endeavors. And to our students out there, thank you for joining us. And next up is your lunch break before our team challenge. So good luck on your challenge. And thanks to everyone for joining us today.
Lunch.